All right, so let's go over these exercises. The first one here deals with the idea of like a pattern in a string. So that is called, I'm calling it here a substring. A substring is like a portion of that string. In this case, we're looking for something consecutive. It's like a consecutive substring. For example, 0, 1, 1, 0, 1. It does contain the substring, and I made it bold and underlined it right there. But these ones, for example, do not contain the substring 110, because if you're looking through these examples, you'll never see a 110. Like, you don't see 110. Here, you have 1, and then later you have another 1, and then you have another 0. So, like, you see those bits in that order, but they're not consecutive, so that does not count. So there's just a little explanation of that. Now, how do we count this? Well, what we could do is start looking at different ways to like arrange the string. There's only 5 bits in the string, and so the 110 could occur right at the beginning of the string, and then we'd have 2 more bits, right? So one possible format is 110 blank blank. Another possible format is to have a bit at the beginning, and then our 110 begins, 110 blank, and have have another blank at the end. So the only other possible format is to have the 110 at the end with 2 blanks at the beginning. So if I draw that, 110. So having written it out this way, I've written it very carefully so that all the bits kind of line up. You can see the first bit, second bit, third, fourth, fifth. And as you can see, there's conflicting bits. So in the first and second cases, our third bit here, those are different. In the first case, it's 0, and in the second case, it's 1. And the first case is also different from the third case because of the fact that that's a 1. Now, the second and third cases agree on their third bit, but they disagree on the fourth bit. So 0 and 1 there. So what that shows, looking at that and like lining it up like this, shows that there's no overlap between these cases. No overlap at all, okay? So these 3 different cases are completely independent of one another, and we can just use the sum rule. Let's just add up the number of possible strings of each format and then add them together. So the way to count that is using the multiplication rule, because we have 2 options for what bit is going to go in each blank. So we have 2 times 2, so it's going to be 2 times 2, that's 2 squared. For the first one, we also have 2 times 2 for the second one, and we also have 2 times 2 for the third one. So we have 2 squared plus 2 squared plus 2 squared. So the total number of bit strings of length 5 that contain that substring I've discovered is 12. So the answer to the first one is 12. So that was just using the sum rule and the multiplication rule, or the product rule. Let's look at the second one. How many bit strings of length 4 start or end with a 1? So again, we can break it into cases, starting with a 1 and then having 3 blanks, right? Because the total length is 4 this time. Or ending with a 1. So that would be 1, 2, 3, 3 blanks and then a 1. Now in this case, there's totally an overlap. So we could like take these and combine them together. What if it starts and ends with 1? 1, blank, blank, 1, right? That's our overlap there. So searching for overlap. In this case, we're going to have to use that subtraction rule, the inclusion-exclusion idea. I was talking about this idea here. Let's see, we're going to have 2 cubed, because each of these blanks could either be a 1 or a 0. So 2 cubed options for the number of different strings that are following the first format, plus 2 cubed different strings following the second format. But now I have to subtract the overlap, right? So I'm going to subtract 2 squared, because the overlap with a 1 at the beginning and a 1 at the end only has 2 different blanks. So 2 squared. So here we have 8 plus 8 minus 4, and that happens to also equal 12. So the answer to that one is also 12, just by coincidence. All right, so now the next question, how many positive integers less than 100 are odd or square? This one, we're not dealing with strings at all, but we could break it down into like the cases again, like we were doing with the previous one. Odd or square, right? So square, so first of all, odd number, even and odd numbers, that's fine. A square number is a number which is a perfect square. Like, I could have written perfect square here. Like square numbers are 1, 4, 9, 16, 25, and so on, right? So positive integers, so the numbers, positive integers less than 100 means the numbers we're talking about here are 1, 2, 3, dot, 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 and then like 98, comma, 99, and then stop. Okay, so it's the numbers 1 through 99 that we're dealing with. So the way I want to approach this is I want to count up the number of odd numbers less than 100, okay? How many odd numbers are less than 100? Well, let's see. Of the numbers from 1 to 100, half of them are odd and half of them are even, right? And so 50-50. And then the number 100 itself is an even number. So the fact that I'm taking out 100 isn't going to change the fact that I have 50 odd numbers in here. So that's 50 odd numbers. Okay, so that's the number of odd numbers is 50. Now let's add that to the number of squares. So I want squares less than 100. How do I count the number of squares less than 100? Well, 100 itself is a square. 100 is 10 squared. So I'm not going to count that one. But any square number before 10 squared is going to be in there. The smallest one I want is 1 squared. So I've got 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6, 7, 8, and 9 squared. And those are the numbers I'm going to be counting up, right? Those are the squares. And then I have 10 squared, but I'm not counting that one. That's 100. I'm saying less, right? So that's 9 different possible squares. So plus 9. Okay. So now that is my adding up odds plus squares, but then aren't there some squares that are odd? Like 1 is a square number and 1 is an odd. 25, right? 25 is a square number and 25 is odd. So that's the overlap. I have to subtract my overlap. So I'm going to subtract the number of integers that are both odd and square. So odd squares less than 100. And how many of those are there? Well, of these 9, how many of them are odd? You've got 1 squared, 3 squared, 5 squared, 7 squared, and 9 squared. Those are all the odd squares, so there's 5 of those. So I subtract 5. And so my answer here, 50 plus 9 minus 5 is 54. So there are 54 positive integers less than 100 that are either odd or a perfect square. Okay, so next, last one. Now this last one I think is the most interesting one because there's a really clever way to approach this. There's 2 different approaches to this. I'm going to talk about the sort of the long way, and then I'll show you a short way. So the question is, how many letter strings of length 4 contain the letter X? Well, it doesn't say just one X. It says like this would be like at least one X. And remember, you're allowed to have repeats. So what if we had like 1X? Well, that could be an X blank blank blank, or it could be like blank X blank blank, or blank blank X blank, or blank 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 X, right? It could be that. What if there's 2 X's, you know? 2 X's would be like XX blank blank, and then like X blank X blank, and X blank blank X, and my gosh, there's going to be a lot of these. Blank XX blank, blank X blank X. Okay, I'm just going to put a dot dot dot, and I'm going to bleh. This approach is fine, but it's going to take a long time, right? Like figuring out all of the different possible formats of like, you know, where could the X's be? And then you've got these blanks, and then each blank has, you know, how many different options are in each blank. It's not going to be 26 because you don't want to have an extra X's in there messing things up. You want to control the number of X's. So each blank has 25 options. But that's the number of things here is going to be huge. So let's kind of dial that back a little bit. Let's step back and think about this a little more carefully. If I want to count the number of letter strings of length 4 containing X, well, maybe what I could do is just find the total number of letter strings of length 4, the total number, and then subtract from that the number of letter strings that don't contain an X. Right, so the idea here is, let me move to a blank page here first for just a moment to draw you a picture. Here's the set, here's the universal set, right? The universal set of all letter strings of length 4. Here's the set we're trying to count, which is the letter strings of length 4 that contain an X. And then what I want to do, let's call that the set A. That's what I want to count. What I'm going to do is instead count this, not A complement. Okay, my union is the whole thing, or sorry, my universe is the whole thing. I want to count A complement, all the things that aren't in A, and then I can use this identity. This is like a set identity. I'm not sure we ever went over this particular set identity, but the number of elements in A is going to be equal to the number of elements in the universal set minus the number of elements in A complement. Okay. This is a set identity involving cardinalities here, right? It's going to be this is at least for for finite sets. A subset of the universal set U. Okay. So yeah, so I'm just taking the number of things minus the number of ones that are not in my set, and that's going to equal the number of things in my set. So what I want to do here, let me go back to the problem. So I want to say, let's count the number of all letter strings of length 4. Okay, the total number of letter strings of length 4 minus the number of strings of length 4 with no x. Okay, so to do that, I have 4 options, right? And each one could have 26 different letters. So if I'm just counting all strings, it's going to be 26 times 26 times 26 times 26. All right, 26 options for each blank with 4 blanks. So that's 26 to the power 4. Okay, now minus. The set of strings that contain no x at all means I'm just going to exclude the x and say x is not allowed. So now I've taken my number of options from 26 down to 25. So I could say 25 to the power 4, right? Because each blank has 25 options. So this is all of them, and 25 to the power 4 is just the ones without an x. And if I do this subtraction, I get 66,351, and that is the number of strings that do contain an x. And that approach, by subtracting the complement, that approach is way, way easier than trying to categorize all the different possible arrangements of strings that involve at least one x in them. Okay, so use this, think of this as like a handy dandy trick that you can put in your back pocket and take out. If something seems complicated, you might be able to simplify it by looking at the complement of the set instead of the set itself.